Today is the day you've all been waiting for. We're going to start talking about Rust, and in particular, all of the memory safety issues that Rust is going to help us avoid. Um, so yeah, I think we are good to kind of jump right into it. Um, we'll start off with some logistics to start us off. First thing, big thing. If you're hearing this right now and you're not on the Slack, be on the Slack. You can go to Canvas and kind of open up the Slack link from there. If that's giving you difficulties or something is weird, you can just email me or Ryan and we could kind of figure that out for you. But super important, we'll share a lot of things, nice community vibes on Slack. So be sure to join. Um, Other big thing is that the week one exercises are due this coming Thursday. If you need additional time, like super chill, just let us know beforehand. And something cool that you can do with the exercises as well is that you could write a blog post instead. So if you're not feeling the exercise or you just want to write as a way to kind of supplement your learning, that's super chill. I think writing is a good way to supplement the learning. So feel free to do that as well. And you could kind of talk through any ideas you might have with either me or Ryan. Um, any questions on like the week one exercises or logistics on that? Cool. So like I said, today is the big day. We're starting off with Rust. We're going to talk about that ownership model that we're going to spend this whole lecture kind of getting a feel for. And we're going to start to see how it's going to prevent these common memory errors. Um, so we've seen like these double freezes after freeze. And if you took a look at that vector exercise that we're going to spend some time talking about right now, maybe you're going to be familiar with some of these memory errors, or in the days of 107, perhaps where you've ran into them a few times. Um, on Thursday, we'll get into deeper memory errors in Rust, some other features that Rust might have to help us out with that. But yeah, so big first thing is to actually identify these memory errors, like what sorts of errors are we actually avoiding, kind of moving to this other programming language. And so we're going to talk a little bit more about that vector exercise. Big thanks to Will for this exercise. I think he teaches 242. Is that right, Ryan?
Yeah,
Programming languages course.
he's not teaching it this year, but he taught it last year.
Cool. So that's a class. But yeah, so we'll kind of put you into some breakout rooms to talk through this vector exercise. Feel free to introduce yourself, kind of talk through errors you found, maybe didn't find, or maybe some errors that maybe aren't errors. Kind of talk through your thinking in your groups, and then we'll come back together and have a deeper dive into what those errors actually were.
Yeah, and if you didn't get a chance to do this before lecture, that's totally fine. But it's on the course website. If you go to the lecture 3 lecture notes, I think, on the course website. So the code is there. If you didn't get a chance to take a look at it, it's okay. Just give it a quick skim and see what kind of problems you find. So let me make the breakout rooms. Let's do like 3 to 4 people. All right. And we'll give it like 10 minutes.
Have fun.
So there's a lot of problems, and some of the problems are like, they should be problems. Like you look at this code and like that's not right, and then they end up not being the primary issue just because there's some other problem somewhere else that's even worse that makes that maybe not so much of an issue. Um, I'm not sure how many y'all found. There are at least 7 of them, and I'll post a list in Slack afterwards. Um, there's things like the initial size of the vector is 0. So then when you go in vec push to try to multiply the capacity by 2, you still end up with like a capacity of 0 because 0 times 2 is still 0. And so that causes problems in vec push, but if you had just like initialized the vector correctly, then maybe we wouldn't have that sort of issue. Or the one that you were talking about, how vec push is actually failing to free. So vec push, when it resizes the buffer. By the way, for those who may be less familiar with vectors, the way that vectors work is that you allocate a fixed size buffer, a fixed size array, and then when you need more capacity, you throw out that array and copy everything over to a new array that is twice the size. This is usually how vectors work. And vec push has a memory leak where when it resizes and copies to a new array, it fails to free the old array, which we're not using anymore. But maybe that's not actually a memory leak, because if you look inside of vec new, we actually never freed an initial array. Like vec.data is just null, And so if there is no initial allocation, is it really a memory leak to discard the initial allocation if it wasn't there? There's like a bunch of philosophical questions here too. Um, and basically the code just has so many mistakes that it's really hard to reason about where should things be done correctly. And we'll talk about this a little bit. Just to overview 4 of the most important bugs that I think that you should be aware of. So one of the simplest to understand, I think, is the memory leak. So this is what I was just talking about, where vec push is allocating a new buffer. That's this new data here that is twice the size of the old one. And then it copies the data over and switches over to using the new buffer. So what this looks like is our vector is pointing to some old buffer, which is full. We want to add a new element. So we allocate a new buffer and copy things over. And then we switch vec data to point to this new buffer. And now we're using the new buffer. But we forget to free this old buffer, so it sticks around, and this is considered a memory leak. It also has some double frees. So if you look in the last 2 lines of main, what it's doing is it's calling free on vec data. And then it calls vec free, which if you look at the implementation of this, also calls free vec data. And so it's actually freeing this buffer twice, which is not so good. And this might sound innocuous, right? It's like, we just called free twice. What's the big deal? Nothing really terribly wrong here, right? But actually, this is a really serious bug that can lead to remote code execution. Remote code execution is when some attacker sends you malicious data and takes control of your binary. Instead of running code in your text segment, now you're running code that the attacker sent you, which is really bad. And my mind was blown when I saw that you could do this because this looks so innocent. But if you take CS155, there's a problem on an assignment there where you actually get remote code execution from a double free. They give you some code that has a double free and they're like, get root access. And I'm like, that's impossible. And then by the end of the assignment, you're like, oh, wow, I have root access. There is an issue with dangling pointers. So what's a dangling pointer? A dangling pointer is a pointer that is referencing memory that isn't there anymore. And I think this one is a little tricky to understand, so I want to make sure everyone gets this. Every program has a stack, right? So we start off with main, and main calls vec new initially, which declares this vec up here. So this first line is allocating space on this stack frame for this vector. And then down here, it's returning a pointer to this vector. So, these 3 lines here initialize the vector with vectory stuff, and then it returns a pointer to this thing here to main. So everything in this picture looks fine so far, except as soon as you return, that stack frame goes away. And then if you look at the code, the next thing that main does is it calls vec push. So it creates a new stack frame with vec push. Vec push has some local variables, so there's some space that's allocated there for the local variables. Except now, if you try to use this vec pointer, it's pointing not to a vector, it's pointing to, I don't really know what. It's just garbage stuff. And if you try to use this data as a vector, you're going to be in trouble because there's arbitrary information there now. So that's not so good. And there's also another kind of dangling pointer in here, which is called an iterator invalidation bug. So an iterator invalidation, an iterator is just a reference to a certain position inside of the vector. An iterator typically starts at the beginning of the container, and then you go through the elements one by one. You move this reference through the elements of the container. And if you modify the container, if you add things to the vector, that iterator can get invalidated, and you're not supposed to use it anymore. But there's nothing in the compiler that prevents you from using it. So here, n is an iterator. It's a pointer to the beginning of the vector. And so here's our vector. It's our buffer. We have n pointing to the first element. And then when we do vec push, if this triggers a reallocation, then we're going to copy things over to some new buffer. Vec data is going to point here. Ideally, this thing should be freed, right? We actually have a memory leak, so this bug maybe isn't a bug because of the other bug. But really, that old buffer should be freed. And now int n is pointing to freed memory. Memory could be repurposed for something else by some other code, so you don't necessarily have these elements here anymore. And if you try to do printf and you try to print out stuff, you dereference this pointer, you are dereferencing arbitrary data. We have no idea what might be here because we already freed it and it could have been reused for something else. Any questions about what these or how these bugs work? So let me ask you a general question. This code is really bad. It has a lot of bugs. It probably has more bugs than things that work correctly. But is there, like, can you tell me qualitatively what is it that makes this so bad? Like, yes, it has a lot of bugs, but is there something style-wise that if you turn this in, your TA would just like facepalm because they're not really sure what to do with this? What makes this code not good? Sure, it doesn't work. It's functionally totally broken. But I've written code that I personally feel is decent code, and it didn't work on the first try. Like there was some typo, some I was missing one line. It was like really close, and I like to think that even though it didn't work, it was decent code, and I did get it to work after I changed like one little simple thing. That's not really what's going on here. You can fix a line here, you can fix a line there, and this code is still going to be is still going to have issues. I think that's a really, really good description. It's careless code. There wasn't a lot of foresight in writing the code. Like, okay, we're going to allocate the memory here. We're going to free the memory here. It's going to be used here. It's kind of just like, we have a vec. I need a pointer to the vec, so I'm just going to take a reference to that and return it, which turns out to cause um, a dangling pointer because it's like not pointing to the right thing, and then you're like, let's reallocate here and let's free here and free here too. Why not? And it's kind of just a little scatterbrained in the approach. It's like there wasn't really a plan in place. There wasn't any structure. And I want to take a step back, actually to 106A, and talk about the Stonemason Carol problem. So for those who haven't taken 106A, this is a problem from the first week of 106A where there's this little robot named Carol, and robot is supposed to place beepers, which are these diamonds, in these columns. So the columns are what, like there's 3 spaces in between each column, so they're kind of 4 spaces apart. And so Carol is supposed to go up and like make sure that this column is filled with diamonds, and then go to the next column and go up and make sure, put a diamond here, put a diamond here, go back down, go to the next column, put a thing here, 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 so on and so forth until you get to the end. And this seems like a very trivial problem now, but for beginning programmers, it's actually very difficult to implement, and it's hard to reason about because you're like, wow, how do I... There's a bunch that needs to be done that is kind of dependent on the situation that I'm in. There's a non-trivial amount of control flow. How do I structure this? And beginner programmers try to fit the whole solution in their heads at the same time. And the key point that we try to drive into 106A students in the first 2 weeks is like decompose, decompose, decompose. Break your problem down into small components that you can reason about in isolation, and then put them all together into a solution that works. And like a natural decomposition for this is while front is clear, so while like we haven't hit the end here, while we haven't hit this wall, repair a column and then go to the next column, and then repair the column and then go to the next column, and repair the column, go to the next column. It's like come up with a high level plan where things fit together nicely, then implement each little building block without having to think about the entire program at the same time. And really this is the problem with our vector solution. Because it's lacking structure and it's lacking planning, you have to think about the entire program at the same time. You have to think about the fact that, oh, while I'm freeing here, this pointer is actually a pointer to this thing on the stack here. When I'm reallocating, like, oh, I have to think about this and this and this. And we don't want that. We want to think about things in we want to think about the big picture at a high level, and then be able to think about the small components in isolation without having to hold everything in our heads. So I've section led 106A a bunch of times, and many students write repair column in such a way that sometimes Carol ends facing south, and sometimes Carol ends facing east. And this causes a lot of problems, because then if your move to next column thing just like moves 4 spaces over and Carol happens to be facing south, you're going to try to move 4 spaces into the ground. And that's not going to be so great, because Carol is going to crash into this bottom wall, and life will not be great. And we try to drive home this idea of like pre and post conditions. You have your preconditions, which are conditions that are supposed to be met before the function starts running, and post conditions, which are supposed to be met once the function is finished. So like the post condition of repair column might be that Carol is facing south, or it might be that Carol is facing east. Whatever it is, it just has to be consistent. Like we have to know, looking at this, okay, after repair column, Carol's going to be facing a certain way. That means that move to next column can expect that Carol is in that position and can like put the appropriate rotate or move commands in order to make this work. So we want to have pre and post conditions so that we can reason about each small piece in isolation. And then if we can verify that like the post conditions of the first function match the preconditions of the next function, and we can just uphold, like if we can just verify that these pieces fit together nicely, then we can just string together the components and make sure that like all the components fit together, and then our program is good. We don't have to think about the entire program, all the little implementation details here and there. We just put the big picture together, and the program is supposed to work. The challenge of this is it's the programmer's responsibility to make sure that pre and post conditions are upheld, right? There's nothing in those function definitions that says like, oh, here you're supposed to be facing south, or usually you put it in a comment, right? You say like post condition, Carol is facing east at the end of this function. And this really applies to CS 107 level material too. If you're implementing things like a vector where you're doing all of the manual memory management, you really need to be thinking about, how am I managing memory in this program? What is the big picture here? In any complex program, you're going to be allocating a bunch of memory in a bunch of places. You're going to pass it around to a bunch of different functions. There's going to be pointers all over the place. Where is that memory supposed to be freed? If you free it too early, then you might have a use after free where other parts of your code are still using pointers to that memory. If you don't free anywhere, then you're going to have a memory leak. And so you need to define at a high level, okay, what parts of my code are responsible for taking care of memory? Who is going to free the memory? Like which specific function, how is it going to be freed? And if you read good C and C++ code, you'll see notions of what is called ownership that started to pop up just naturally, because people are like, okay, we need to define how this memory is supposed to be used over the last 30, 40 years. They actually use the term ownership. It's not really well defined anywhere. It's just people that are trying to put pre and post conditions on manual memory management code. But we can take a look at some of these examples. So this is from a project called Open vSwitch, which is actually from here at Stanford. And I don't really know what it does. I didn't read the whole code base. I just did some control Fing on GitHub. But it says that it returns some information. It stores, so this function is allocating a string and storing a pointer to it in this error p. And the caller is responsible for freeing error p. Okay, this is the post condition. Like the caller is responsible. I am allocating some memory here. You need to free it. This is stated in the comments here. You call free to free it. Here's another one. This is from a project called FFmpeg. It is passed this dictionary, and it says the caller still owns val, this part of this dictionary, and is responsible for freeing it. So you're passing me a pointer to something, but I'm just taking a look temporarily, and I'm doing a little bit of stuff with that. But actually, it's still your responsibility to free it. I'm not going to free this memory. So make sure that you free whatever memory you're passing me. This one's a little bit different. So here is a function where some data is being passed in. And it says that you don't have to, like, you're passing in a pointer to some memory here. Don't worry about freeing that memory anymore. I'm not going to free it either. You're not going to free it. But actually, I'm passing it to some other component of this code base called the boot sysfs lib, and that component is responsible for freeing it. It's like clearly defined in the comments. Okay, you don't have to worry about freeing this. I'm not going to free it right now, but it is going to get freed eventually. I'm going to hand it off to this other component of the code base, and that has ownership of this memory. It is going to make sure that this memory gets cleaned up eventually. This stuff gets really complicated sometimes. So in the past 3 examples, memory just gets cleaned up by calling free, and that's what you're used to seeing in 107. But sometimes things have their own custom cleanup functions. And we sort of saw this in the vector example where there was like a vec-free function. That's pretty common in C and C++, where you might have a struct with a pointer that points to another struct with a pointer that points to another struct. And if you just call free on the first struct, free doesn't realize that there are pointers to other structs that also need to be freed. And so you have a custom cleanup function that knows that, okay, before I free this, I have to go in, look at the pointer, free the thing that it points to. But before I free that, I have to go in and free the thing that that points to. There might be a chain of pointers, and we have to make sure that everything gets cleaned up. And so you are not, so it says the caller owns the data in port. That means the caller is responsible for freeing this memory. But if you call free on it, that's not right. You actually need to free it using this custom function when it's no longer needed, which goes through a series of pointers and frees a bunch of different information. If you were to call free here, that would cause a memory leak, because you would only be freeing like only one of the structs, and it might point to other pieces of memory that also need to be freed. Here's another one where it says that in order to free it, you have to call this other free function. Same sort of situation. And it gets even worse. But this is all like good code, by the way, that I'm showing you. It's just that manual memory management gets really complicated. So here we're being passed a dictionary. And it turns out that one part of the code base is responsible for freeing the keys of the dictionary, and a different part of the code base is responsible for freeing the values of the dictionary. It might be the case that we use the dictionary for some time, and then after that, we don't need the values anymore, we only need the keys. Or maybe vice versa, where we use the dictionary for some time, and then the keys are no longer important, but we just care about the values in the dictionary. So we free the keys, and then somebody else is responsible for freeing the values. And that's what's happening here, where it says that some other part of this code is going to free the keys, but we are responsible for freeing the values. And this stuff is like really hard to reason about. It gets really complicated, but this is the nature of manual memory management. Like real world code is not always simple. There's a lot of complexities. And so you need to be explicit about who is responsible for doing what. There has to be some notion of ownership, like, okay, this memory is being allocated here. It's being passed to this other component of the code base here. You now have responsibility to free it. Or I'm allocating some memory, I'm passing it to this portion of the code base, but only temporarily. That part of the code base, it might be some helper function or something that does some stuff. I still retain ownership, and I'm still responsible for freeing that memory. Does this sort of make sense? This like primitive notion of ownership, of like delegating responsibility to different parts of your code base? I always anthropomorphize my code. Like this is how I think about programming, is I'm like, oh, I'm a function. I'm going to like hand off this value to this other person, this other function. And I think the ownership model really is aligned with anthropomorphizing your code. As you think about, okay, I'm this piece of this code base. These are my concerns right now. This is the details that I have to think about. I'm responsible for this memory. I have to clean it up. Or, oh, I'm giving this memory to somebody else. They're going to go ahead and clean it up and do that. But you have to actually like specify this somewhere in your code, in preconditions and postconditions. And it's up to you to make sure you get this right. Like you can write in your function comments, this function takes a buffer and it does not free it. You still retain ownership. You need to free it. And then the function calling that has to like read that comment and know, okay, I need to free this. Otherwise, we're going to have a memory leak. If you don't get this right, so in 106A, your program can crash. In 107, if you don't get this right, your program won't necessarily crash. It might appear to work perfectly fine. But if somebody figures out your mistake, if an attacker figures out your mistake, you can have anything from a memory leak. So a memory leak, if you leak enough memory, your program will just crash because you'll run out of memory. So maybe not that bad, but also definitely not great. Or if you have double freeze or use after freeze or buffer overflows or a number of different memory errors, you can have remote code execution, which is really bad, where an attacker will actually take control of your program. And the compiler can't help you out. We talked about static analysis, but if you do the week 1 exercises, you'll see it has some severe limitations. And the key point, this is what I want you to take away from this portion of the lecture, is the compiler does not know what your post conditions are because it's not expressed in the C language. You can write your post conditions and your preconditions in comments, but the compiler has no idea how to read your comments. And there's nothing in the C language that says this function is responsible for freeing this memory, or this function is passing this memory to some other function and that function is going to free the memory. There's nothing like that in the C language. The compiler doesn't know what you're talking about. And this comes down to what is a type system of a language. So the types of a programming language are the nouns of a spoken language. It's when you talk, what do you talk about? In a programming language, you have ints, and you talk about ints in your programming language. You're like, okay, this function takes an int, it returns an int. The C type system has numbers, pointers, and structs. There's not that much else. Like when you write a C program, this is what you're talking about, and maybe functions too. So you have a function that takes a number and it returns a pointer and allocates some memory, and that's mostly all there is to it. It's very simple. You can learn basically the entire C language in half a quarter of CS 107. Simple does not necessarily mean easy, because you might have complex thoughts of like, okay, we have a list, and there are things inside of this list that have like particular attributes, but you have to translate all of this into like a primitive language that doesn't really have many nouns. It's a very small type system. And this leads to things like stir-dupe. So the stir-dupe definition, it just looks like this. This is the C code, right? It takes a string and it returns a string. Actually, the compiler doesn't even know what a string is. It just knows that you have a pointer to a sequence of characters. So it takes a pointer to a sequence of characters and it returns a pointer to a sequence of characters. If you use this incorrectly, you might have some string and receive this in a char star, and then you return. And the compiler will analyze this and it will say, hey, you passed a sequence of characters to stir-dupe. You took the return value and stored it as a sequence of characters. Everything looks good. Nothing wrong with this code. But if you know something about stir-dupe and you actually read the comment, it says it's allocating memory for a new string with malloc, and that memory should be freed with free. So an experienced programmer will look at this and it will say, okay, we are receiving a heap allocated string from stir-dupe. That's this variable here, this duplicate variable. And then we return right away and we didn't free the string. Like an experienced programmer, based on what you know about stir-dupe, can look at this and say, hey, that's not right. But the compiler doesn't see this. The compiler doesn't know this part of the man page. It has no idea how to interpret this like free English text. It doesn't understand that there's actually a post condition here, which is that you have allocated heap memory which needs to be freed by somebody. And we're not freeing it. Does this make sense to everyone? So again, you can write your pre and post conditions in the comments, but if they're not in the actual code, like if the language doesn't give you a way to express those pre and post conditions, then the compiler doesn't know what you're trying to do. It can verify the basic types. It can verify that you take a number. It can verify that you take a Boolean. It can verify that you return a pointer to a sequence of characters. But beyond that, it doesn't really know your intent. It doesn't know what you're trying to do, so it can't give you an error if you do something that you didn't mean to do. And the key question of this class is, are there better type systems that we can use to actually specify our intent in the code in a way that the compiler can understand? Because if the compiler is able to understand your pre and post conditions, if it can understand that you're returning a pointer to heap allocated memory that needs to be freed by somebody, and then it can actually go and check that, oh, hey, somebody did call free on this, then it can verify that you met your pre and post conditions and that your code is looking better. And this is really what we're trying to get out of Rust. So Julio's going to kick us off by giving a high-level overview of how some of this appears in the Rust language, and then we're going to do more of a deep dive on Thursday.
So the big question that we're going to kind of talk about now, we've heard ownership. We see that it can exist in comments in C, but nothing really forces you to like free your memory. But what if that ownership actually lived in the programming language? So here's your first line of Rust. You have let Julio equals bear get. And so this might look like a familiar line. We have some sort of declaration of a variable, in this case Julio, and it's equal to some function return. In this case, you can imagine it's just giving you a bear. And the first thing I want you to imagine when it comes to ownership and in Rust is that every single variable, in this case Julio, owns that bear. Like, this bear belongs to me and no one else, and I can do what I want with the bear. And specifically now, since I'm the owner of this bear, I am responsible to put this bear back. So you might imagine maybe we're in like some sort of like daycare or some place where like there's a bunch of toys and you're given toys. Once I play with my toy and have like the fun that I want, once I'm done with that, I need to put it back to like where I got it from, in this case the toy cabinet. In terms of code, what that might look like is a little function here like main, where we have let Julio equals bear get. Once this function returns and the function is done, then Julio, I am the one who is going to put the bear back, and no one else is going to do that for me. Any early questions or thoughts about this idea of kind of owning an object like this? Fantastic. So just a quick recap of all of that. Julio, or the variable name, is the owner of the object on the right hand side of the equal sign. I can do anything I want with this toy. So maybe it has like a button to light up or something. Maybe that's like a function you can call on it. And those functions, those methods, I can call on the bear. And the big point that we keep coming back to is that I, Julio, am the one responsible for putting this bear back and freeing that memory. So things get a little interesting now when we add another line to this program. So we start off with let Julio equals bear. Julio has the bear. Then afterwards, if we add a line like let Ryan, some other variable, equal Julio, this is what I want you to envision now. So initially, Julio had the bear, but now the bear has moved on to Ryan. So we can take a look at Ryan a little more deeply. Now Ryan is the owner of this fantastic toy, and now Ryan can do everything that Julio could do before. So we're talking like all the functions, press the button, make it light up, anything that you could do with the bear previously that Julio could do. Now Ryan is the one that's able to do that. And importantly, Ryan is now responsible for putting that toy back in the shelf, freeing the memory, putting it back. And that is all on Ryan instead. So the interesting question I'll pose to all of you is, what happens to the Julio variable? Does anyone have any ideas as to what might happen now if Ryan owns this bear and now maybe Julio doesn't? That is a fantastic question. We'll get a little bit more into like the memory representations on Thursday. Right now, what you can imagine, what you all can imagine, is like the bear is some value attached to Julio, and now it has moved on to Ryan. And so we have some messages in the chat. Julio can't do anything with the bear. It's over for me, and that's exactly right. So if we take a look at now the Julio variable, I don't have the bear anymore because I've given it to Ryan. So no ownership, and I can't do anything. In this case, it says string, pretend it says bear. But nothing that I could do before, I cannot do it now. And any attempt to do so would lead to an issue in Rust. But the good thing is that I no longer have to free the bear. I don't need to put the bear back into the shelf. Don't need to free that memory. That is no longer my responsibility. That is now Ryan's responsibility, and I can move on with my life, happy that I don't need to free memory. So you can start to see how these pieces are going to start avoiding these memory errors that we were talking about, is now it's delegated that Ryan is the freer of this object that we now have, and it is not me. So we could actually see this run in a quick Rust example. And so the bear has now transformed into a string. So we have let Julio, which is the variable, equals to, you can imagine this right-hand side is the bear, but it could be any object that we might hold. And in this case, it's the hi friends string. And right afterwards, we said let Ryan equal to Julio.
So just like before, you can imagine that this bear is now in Ryan's possession. It started off in my possession, but then I gave it to Ryan. And so if we try to print out the value of Ryan, this print lin with the exclamation point is how you print in Rust. If we go ahead and run that, all is well in the world. Ryan is the owner of the bear, therefore we can print hi friends and everything's chill. But what is maybe not so chill is if you try to print with the Julio variable right afterwards. So in maybe any other language that you've seen before, you might expect this to print hi friends twice, because they both equal the same thing and all is well. But in Rust, it has that realization that this bear, this string, this object no longer belongs to the Julio variable. And it kind of tells you, gives you a lot of interesting sentences about like why that is, and we'll talk about all of these things. But it really starts off with the borrow of moved value Julio, where the Julio value has moved somewhere else and you're trying to use that same variable again, but you don't own what you have. It is now gone. Yeah, so one way you can envision it is the Julio variable kind of has reference to the object, which is the bear or the string. And so when we try to print it, what the print function is going to want to do is kind of print out what Julio owns. And so at this point, though, Julio doesn't own anything anymore. And so it only works for when Ryan is the owner now.
Are you asking about the compiler error message? How it says like you borrow moved value Julio? So it doesn't really know, the compiler, it's just the best way that it has to say like the thing that you had inside of the Julio variable has been moved out now. Yes. Yeah. Right.
Yep. So you can almost envision that Rust is kind of watching very closely, like, okay, Julio owns something, and now what was in Julio has now moved to Ryan. So if Julio ever tries to like use this variable name again, or if this variable name is used in the future, I've realized that that has moved already. And so that compiler is really watching all of your movements, watching all of who owns what, so that the compiler can give you some pretty nice error messages to make these things kind of easier to find. Yeah, does that answer your question? Sweet. Any other questions on this example, ownership, or anything that I've said so far? That is one way to think about it. You can imagine that the value has now moved on, but something that we can still do is assign Julio to own something else. So like, for example, if I wanted to now let Julio equal some other thing that it could own, then that's okay, because now like the actual object on the left hand side, or in this case myself, can have something else, and maybe now Ryan has the bear and now I have another bear, and that would be fine to do, so long as each thing has one owner. Does that answer your question there? So, any other questions? We have a message in the chat. Aren't variables const by default? Fantastic point. We'll talk a little bit more about like the const and mutability rules in Rust on Thursday. But for now, we could kind of think just high level about like this ownership model. But cool. So we can kind of wrap up really fast with just one more case of where this sort of ownership model is seen. So we've seen it once with this variable declaration. We have one variable, we declare another variable to be that one, and the ownership has not transferred. When else does this happen? It also happens for functions. So in this little code snippet, Julio has the bear get and calls a function, my cool bear function, passing in Julio. And so in this case, now you can imagine that the function is taking ownership of the bear. It has taken the bear from you in the same way that Ryan took the bear from me earlier, such that now any attempt to do anything with Julio, like print or whatever else, also isn't going to work. But the benefit being that now the freeing responsibility has now been delegated over to the function. So now the function needs to be the one to free that information no longer this main piece of code. Any questions on this idea of now functions being able to have ownership? Cool. So yeah, one big concern that comes up with something like this is like, well, how will I ever decompose again? Like Ryan was just saying 106A teaches you about decomposition like in the first 2 weeks. And now I just told you that if you pass a variable to a function, you lose ownership and you can't use it anymore, which kind of kills any decomposition that you would ever want to try. But fortunately, Rust has another feature called borrowing. So you can imagine here, maybe I own my toy, and maybe I want to give it to someone else for just a little bit. Maybe they could do something with it, they could print it, whatever. Then afterwards, they should give that back to me because it belongs to me. And so you can imagine here, we have let void equals bear get. We call the function, but this time with an ampersand. And what you can imagine ampersands get a little confusing with C, like am I passing the address now or something like that. The way to see it is just saying that we are now passing reference. But a better way to see it is that we're allowing the function to borrow our bear, borrow our string, borrow our object, such that when it returns, that bear is now back in my possession, and then I could program as I've normally programmed in the past without having to think that I've lost this variable in any way, shape, or form. So here's like the quick dialogue. You could borrow it, but you have to give it back. All the responsibility of freeing is still on that main owner. It was just for a quick second that someone else had that bear. So with something like borrowing and these ampersands, you kind of get back into that decomposition that you all know and love. Like that time I let my friend have my DS, yes, but theoretically they'd give it back, and so then you would still have your DS, and that's what would happen in Rust borrowing. Any questions on borrowing and ownership or anything like that? Cool. All right. So here's like the big picture of what ownership is. This is in the Rust book. We linked this in the slides. Rust book is fantastic. It explains everything that you can think of. But essentially every single value in Rust can only have one owner. And when that owner goes out of scope, like you saw earlier in the main function where it hits that brace, that's when the value is freed. And so you can imagine all the freeing is happening kind of internally in Rust as it starts hitting these braces. And it decides who should free it based on who is the owner. Like the owner is the one that's going to be responsible for freeing, which kind of helps with that double free that we were talking about earlier. The last big reminder to kind of take home is all of this stuff is happening at compile time. Like your programs are not running. Like you saw in that string example, the compiler like didn't even let us like continue. It was like, hey, you just broke the ownership rule. I don't know what you're trying to do here. And that's like the benefit of Rust, where all of these things are baked into the compiler. Compared to in those C examples we saw earlier, maybe C is okay with letting your program compile when you're not freeing things, because those sorts of checks aren't baked into the compiler like it is in Rust, which does help a lot with these sorts of memory safety issues. But yeah, so that is about it for this lecture. For next time, we'll talk a little bit more about other variables that we can make in Rust. We'll see some other memory issues that are avoided with this sort of system that we're starting to develop, and we'll take a look at some more code examples. Yeah, that's a fantastic question. By the way, for anyone who needs to leave, you are free to go. This is end of lecture. To answer that question, there still definitely is a stack and a heap. We'll talk a little bit more on Thursday about how things are arranged. But you can imagine like the bear in this example like is on the heap, or the string that I showed on the example there. Like those variables are on the heap. And you can imagine that that left side, like the Julio, the Ryan, or something else like that, is on the stack. And so it's very similar to having like pointers to the heap, just like in C. Like that same kind of model is still okay. You can just imagine that there's more rules enforced on that model that exist underneath. Does that make sense? Any other additional questions on anything ownership? It's definitely a little weird, and the first few times you're gonna fight with the compiler for a while. But I think the big idea picture here is to kind of have the foundation of how to think about these things, and then it'll make it a little easier kind of moving forward.